Hey there guys, Mr. Carlson here. Let's take a look at an example where we have a horizontally launched projectile. In this example, we have a stick person here is going to be our horizontally launched projectile. So he's going to be doing some cliff diving here. We've got a 15-meter high cliff and we've got some water down here. So he's going to be running along, and we know that he's running at a speed of 5 meters per second is the velocity that he has when he leaves the cliff. Now we know that for anything that is going to be going off of a cliff or being thrown or whatever, that it's going to have some sort of trajectory or some sort of path that's like this. It's going to have some sort of parabolic arc like this. It's going to be a projectile essentially. Now, for this type of problem, we're saying that there is no angle. He's not going to jump up like this, so he's not going to have an angle to that arc. It's just going to be a horizontally launched. So he's just going to run straight off, not going to jump up. So his motion this way is completely horizontal until he leaves the cliff, and then he starts to fall down because gravity takes over. Now, a couple of key things when solving a problem like this, when looking at problems where it's a horizontal projectile. And the first key thing is this. We need to understand that we have two different things going on. We have going in this direction, something happening, and then we also have something in this direction happening, and they are happening independent of each other, meaning that the horizontal this way, going this way, the horizontal motion is going to be independent of the vertical motion. So what we mean by that is whatever is happening, whatever type of motion is going on in this plane this way horizontally is not going to be affected by the motion that's happening vertically. And same thing, vice versa, the vertical motion going up and down, whatever motion is happening that way is unaffected by whatever motion is happening this way. And so I can look at those two things separate from each other. So for example, let's say that a question asks something like, how long will it take to reach the water? So in other words, after he leaves the edge of the cliff, how many seconds are going to pass before he makes it to the bottom? So to solve that part, what we have to realize is that really him running off the cliff and falling is actually no different in terms of the vertical motion, is no different than if he were to just simply walk and drop straight down. So for him to run straight off this way, or for him to just simply step off the cliff and fall, he would reach the water in the same amount of time. So him running this way and falling, or him just simply stepping off, it would take the same amount of time. He's just simply a free-falling object. That horizontal motion of him running this way is not going to affect how fast that he falls this way. He's still just going to be a free-falling object no matter how fast he runs. He could run at the speed of a bullet going this way. He's still going to fall at a rate of negative 9.8 meters per second. That horizontal motion is independent of that vertical motion, okay? So to solve how long it takes, well, a couple things. We know that he's going to be falling a distance of 15 meters. So I'm going to put over here, so his change in position from here to here is going to be negative 15 meters because I'm going to make this the 0 point and this going downwards. So his change in position is going to be negative 15 meters. And I'm going to say that his initial velocity, and here's how I'm going to write this, I'm going to put a y next to it because typically the vertical axis is the y-axis. So I'm just going to put a y next to it saying that his initial velocity in the vertical direction, so not the horizontal direction, but the vertical direction, his initial velocity would be 0 meters per second. Because if I think about the moment he steps off, so once he gets to like right here, as soon as he steps off the cliff, he's not really going to be falling. He's not going to have a velocity at that moment. It's going to take a few seconds as he's moving before he starts to gain some velocity as he starts to accelerate downwards. So that initial velocity this way is actually going to be 0 meters per second. And then as he falls, the longer he's in the air, of course he's accelerating, and so the faster and faster he's going to go. But that initial velocity up and down is 0 meters per second. What else do we know? We also know that in the vertical direction, so the acceleration, and again we can put y here, the acceleration up and down is, since he's a free-falling object, negative 9.8 meters per second squared. Acceleration due to gravity. And that's all we really need, because if we look at our kinematic equations, we have this equation right here. We have displacement is equal to the initial velocity times the time plus 1/2 AT squared. Well, I have everything I need in order to solve for the time, don't I? Because I know the displacement, I know the initial velocity, and I know the acceleration. I can plug those things in and just solve for time. So let's plug in those numbers. We have negative 15 meters. Now this part of the equation can actually just go away because my initial velocity is 0, and anything times 0 is just going to be 0. So I can cancel that part out. I don't even need that part of the equation. And I'm going to have 1/2 times negative 9.8 meters per second squared times the time squared. And so now let's do this one step at a time here. So we're going to have negative 15 again. We're going to have negative 4.9 when we do 1/2 times negative 9.8 meters per second squared times t squared. So I'm going to divide this side by negative 4.9, bring it over here. Let's see, I got to punch that in real quick. 15 divided by 4.9, and we get 3.06. It's going to be positive because I've got a negative and a negative here, so 3.06. Now our units would actually be seconds squared because we're dividing meters by meters. Those are going to cancel out, leaving us with just seconds squared. And then we're going to have is equal to t squared. So now I just got to take the square root of each side to get the time. So square root of 3.06, and I get a time of 1.75 seconds. So that's how long he would be falling for. As soon as he leaves the cliff, it's going to take him 1.75 seconds to reach the bottom. And again, it doesn't matter what his initial velocity is this way. He's a free-falling object, and so that horizontal motion is independent of this motion. He's going to take 1.75 seconds, whether he's going 100 miles an hour this way, or if he were to just simply step off the edge, it's going to take him 1.75 seconds to reach the bottom. Now, a second part that a problem might ask you, they might ask you, how far from the cliff will he be when he lands? Or in other words, really, what we're looking for is, what's the distance he's going to be from where he leaves the cliff, which would be right here. What is this displacement is essentially what they're asking. So how far is he going to travel in that case? Now, to solve this part, what we have to realize is that we're looking at a horizontal direction. We're looking at his displacement horizontally, and so therefore the motion that's happening vertically is not going to be affecting that horizontal motion. So the fact that he's accelerating this way has zero effect on the fact that he's going to be moving at 5 meters per second horizontally. So whenever we're dealing with problems like this, the horizontal motion is always going to be at a constant velocity. This is going to be a good thing to remember for problems like this. So whenever we have projectile problems, the horizontal motion is always at a constant velocity, but the vertical motion is always going to be accelerating. And the acceleration is always going to be that negative 9.8 meters per second. So he had 5 meters per second for his velocity as he was running this way. So now what I'm going to write is that initial velocity in the x direction, the horizontal direction, is 5 meters per second. The other thing that we know is what we solved for previously. We know that he's going to be in the air falling for 1.75 seconds, because that's what we figured out. For him to fall from here down to the water, it would take 1.75 seconds. So that's how long he's going to be in the air. That's all I need to solve for the distance that he goes, because this is a constant velocity, and there's really only one equation that I can use for something moving under constant velocity, and it is our velocity equation. Velocity is equal to the displacement divided by the time. I can't use any equation that involves acceleration because he's not accelerating in the horizontal direction, but I can use this. I know the velocity that he has the entire time. He's going to be moving at 5 meters per second in this direction for that 1.75 seconds. So if I rearrange this to solve for displacement, it's simply just going to be the velocity times the time. And so his velocity is 5 meters per second. And we're going to multiply that by the time that he's in the air, 1.75 seconds. And let's see what that works out to be. 5 times 1.75. And I get a displacement of 8.75 meters. And so that's how far he would be from the base of the cliff. So the main thing to remember about problems like this, the horizontal motion is independent of the vertical motion. And the vertical motion is always accelerating, but the horizontal motion is always a constant velocity.